Let's review what we learned so far about vertical asymptotes versus removable discontinuities. These are both different kinds of discontinuity. This is often called an infinite discontinuity. So these are kind of two very simple examples of equations that produce each of these types of discontinuity. So here I've got something divided by itself, so you know that simplifies to be 1. But writing an equal sign is not quite right here because x equals 1 is not part of the domain of this function because it would give us 0 over 0, which is undefined. So it equals 1 for all x values not equal to 1, but it's not defined for x equals 1. So if I was going to imagine it as a graph, the graph looks like this with a hole right there, a removable discontinuity. So that's this side. Here, you recognize this as a transformation of the reciprocal family, the 1 over x family. So here I've got a 1 over x function that's got two asymptotes, but I've shifted it right by 1. Excuse me. But I've shifted it right by 1, and I've scaled it by 5, because this is equivalent to 5 times 1 over x minus 1. So when I shift the whole thing right by 1, the vertical asymptote shifts over to 1. Everything else remains the same. Vertically scaling it is going to change some of the y values here, but since I didn't label my y-axis, you can't tell. Okay, so far so good. So why did this side end up as a removable discontinuity instead of a vertical asymptote? You can think about it this way. Both a removable discontinuity and a vertical asymptote are the same in a certain sense if you're only looking at the value x equals 1. Because at the value x equals 1, both of these functions aren't defined. So the difference between these two situations doesn't have anything to do with the value where the discontinuity is happening. It only has to do with what are the y values of the function doing as you get closer and closer to the undefined value, to the undefined x value. So here, if I was going to make a data table where x starts at 2 and then gets closer and closer and closer to 1, you can see from the graph, obviously, that the y values are just always equal to 1, because here I've got 2 over 2 is 1, and 1.5 over 1.5 is 1, and same, 1.001 over 1.001 is 1. So it doesn't matter how close x gets, the y values are always 1. If we were going to write this in limit notation, let's define this as the function f of x. We would say the limit of the f function as x approaches 1 from the positive side equals 1. And that's just a way of saying that as the x values get closer and closer to 1 from the positive side, so from values that are larger than 1, the y values are getting closer and closer to 1. And remember, it doesn't matter what happens when you actually get to 1, because limits aren't about what happens when you get there. Limits are about what happens as you get closer and closer. For this particular example, the right-hand limit here is the same as the left-hand limit. So the limit as x approaches 1 from the negative side of f of x is the same. So all three pieces are the same. Sorry, not three pieces. Both of the limits, both the left and the right-hand limits are the same. So what's happening on this side for the y values as x gets closer and closer to the point of discontinuity? So let's plug it in. So in my work column, I'll have 5 times 1 divided by whatever minus 1. So 2 minus 1 is 1, so that gives us just 5. Here, I've got 5 times 1 over 1 minus 1/10. So 1 minus 1/10 is 1/10. And so 1 divided by 1/10 is the same as 10. So this is actually 50. Here I've got 1 over 1 minus 1/100th, which is the same thing as 1 over 1/100th. So again, this is like 5 times 100, which is 500. This one is going to, you probably sense the pattern here, this one's going to be 5,000. So what's happening is, as the x values are getting closer and closer to 1, the y values look like they're getting larger and larger, approaching infinity. And that's why this particular example is producing the vertical asymptote there. It's because as the denominator is getting closer and closer to 0, the overall y value is getting larger and larger, which is what's forcing the curve up towards that asymptote. So using limit notation, we'd say that the limit of the f of x function, I guess I didn't define it here, so let's say limit of the 5 over x minus 1 function, as x is approaching 1 from the positive side, I was recommending that you write increases without bound. Although in some textbooks, you'll see this written as equals infinity. And the only reason I don't want you to do that is because this makes it look like infinity is a number like other numbers, and it's sort of a special value. In particular, later on in calculus, you're going to define functions that are equal to limits, and a function can't have infinity as an output. That would be an undefined value. That point wouldn't be in the domain. So we don't want to get in the habit of pretending like infinity is a number like the other numbers. So you can use this idea to take any function that you want and put in discontinuities if you wanted to. So we could take like the x squared function and we could add a removable discontinuity wherever we want, or a vertical asymptote wherever we want. So let's pretend we wanted to add a vertical asymptote at 0. You just have f of x times 1 over x, because you know that 1 over x has a vertical asymptote at 0. So your equation, well, here, let's do the other one first. Let's say we wanted to add a removable discontinuity at 0. We would have f of x times like x over x, for example. And that would put in the removable discontinuity. So this one we can graph right away. This one, x over x is like a fancy form of the number 1. How do I write a 1? Is it like this? Does that look like a 1? So notice that if f of x represents the output, it's the y value. So if I'm multiplying the y value by the number 1, it's not changing any of the y values. So I know that these two graphs have the exact same y values at the exact same places everywhere, because I'm only multiplying by 1, except at x equals 0, and in that case, I've got a well-defined number times something that's undefined, which is what creates the hole there. On this side, however, we're not going to have the exact same y values, because putting the vertical asymptote there is going to force the curve either up or down towards the asymptote, and doing that is going to adjust all of the other y values. So none of the y values in the resulting function are going to be exactly the same as those of the original. So here we would expect to see something like this maybe, except if this function originally was x squared, let's think about what would happen. I'd have x squared times 1 over x, and that actually would simplify. So like x squared divided by x, that simplifies just to be x, right? So actually this wouldn't produce a vertical asymptote at all in this case, because we would be able to simplify it. So this would actually be the line y equals x with another removable discontinuity there. So there's some nuance involved in applying this idea. What produced the vertical asymptote in the other example was the fact that the value in the denominator that produced 0 was not actually a factor of the numerator. Like, you couldn't simplify out that denominator. And in this case, we could simplify out the denominator. So let's change it a little bit. What if this is actually x squared plus 1? So let's move it up. So now if I have x squared plus 1 times 1 over x, now the x is no longer a factor of the numerator, so I can't simplify it away. So here I really will have something that looks like my original quadratic, except that it's going to be forced this way. Let's actually just check it out on Desmos real quick. So there you can see, similar to what we sketched, we've got the x squared plus 1 divided by x. So what's your takeaway? If you looked at the original example where we have 1 over x minus 3 and you said, aha, whenever there's x minus 3 in the denominator, that means vertical asymptote at 3. That is not quite the right takeaway because you have to look at the context of the whole problem. So think about this. If I've got a function f of x and I divide it by x minus 3, under what conditions would this have a vertical asymptote and under what conditions would it not? If you can answer that question, then you've got the takeaway. So if the function does not have x minus 3 as a factor, then that means it's not possible to simplify away the x minus 3, and that means that there would be a vertical asymptote. So if f of x was equal to 1, if it was equal to x squared, anything like that. But what if f of x equals x squared minus 9? So this function, so if my f function is x squared minus 9, this one would not have a vertical asymptote at x equals 3 because x squared minus 9 factors as x plus 3 times x minus 3. And then you'd have the x minus 3's canceling each other. So that would be the same as if I'd written this. So this function, you shouldn't think about it as f divided by x minus 3 because it's algebraically equivalent to this line times the fancy form of 1, which was characteristic. I don't know how to draw 1, which was characteristic of the removable discontinuity. So that's the takeaway. It matters whether or not the factorization of your rational expression matters, because if you can pull out a fancy 1, then that means you've got a removable discontinuity instead of a vertical asymptote.